The sun isn't technically the center of our solar system. It's in a space called the barycenter. It depends on which planet you're standing in. The barycenter is usually closest to the object with the greater mass. So, since we're on Earth, the true center of the solar system is the sun, but not the center of it. With respect to Jupiter, the barycenter is actually outside the sun's surface. Jupiter is 318 times bigger than Earth, so the balance is different. The planets don't really revolve around the sun, but around their common center of mass. Imagine balancing a pencil on the tip of your finger. You'd have to place it right in the center so that it doesn't tip on each side. Because the pencil has its mass equally distributed, it's easy to assume that everything balances its way like that, especially in outer space. But try balancing a hammer on the tip of your toe. Chances are you'll walk out of here with a broken toe. Its true barycenter is close to the hammerhead rather than the actual center where you'd grip it. Earth and the sun's barycenter is like that hammer. The center of mass is more or less in the center of the object. Realistically, if the sun were to rotate around Earth, then our little blue planet would have to be just as big as the sun, or bigger. We can't disregard the other planets in our solar system, which means they all will have to rotate around us as well. But in the ancient days, bright minds always thought everything revolved around the Earth. They called this the geocentric model, and this made sense to them because it looked like everything above us was spinning around us. The sun and the moon played vital roles in human history, and we didn't feel insignificant in the universe until way later on. In ancient Greece and the Middle Ages, the big brains used the geocentric model to study space. It wasn't until the 16th century that that model changed. Back in those times, they couldn't even imagine that everything revolved around the sun, and they didn't have the knowledge to back any of this up. The Earth can't be the center of the solar system because it's not large enough for the job. For the conditions to suit the enormous size, life would have evolved differently. We'd probably be less dependent on oxygen. Some animals, like whales and dolphins, can stay for hours without taking a single breath. They can even sleep underwater. So the humans of the sun-sized Earth would have specialized lungs and wouldn't need to constantly be taking in air. It means that the plant life would be limited, with just a few shrubs here and there. There are trillions of trees around the world, but the main contributor to producing oxygen is the algae in the ocean. With such vast real estate of oceans and seas, the algae sitting on top are pumping out the air we breathe. Oxygen wouldn't be so abundant on this planet, but our breathing mechanisms might rely on carbon dioxide, another common gas found on other planets. If the planet is hot, then water will be scarce. We would only find it on certain parts of the planet, like mountaintops. The ground would be too scorched for anything to survive in properly. We can forget about seasons as well. The sun is currently just large enough to give us what we need. But since the Earth would be so large, and the sun would be another celestial body emanating heat, we'd always feel like we're inside a microwave. The days and nights will be different, and not much precipitation will happen. With so much heat produced in the core, earthquakes and volcanoes would likely erupt all the time. The surface would practically be a scorching plain of red magma floating around. This would be the true red planet. But if we had the same landscape like on Earth, living somewhere near the mountains could save you. The mountains would still be embedded in the core, but it would be better than staying on the ground. Some of the mountain peaks could even be 100 times taller than Mount Everest. The canyons could be so deep that the Mariana Trench would feel just like a little rupture. Animals would also behave and look different. Cold-blooded animals would have to soak up as little sun as possible so they don't burn. Animals would have to rely on migration to find water in distant lands. Birds can fly for hundreds of miles for migration season, so we'd probably see certain sleek-looking birds speeding through the air. But because gravity would be so strong on the colossal-sized Earth, the flying animals would need thinner bones and a thinner core just to take flight. The real survivors would be the microorganisms. They can live in extreme temperatures and pressures and can live without oxygen for a good while. The nights would be dark since there wouldn't be any moon to reflect the sunlight. The moon would most probably be on the opposite side of where the sun is shining, so it would forever be a floating ball in the sky. The Earth's rotational speed is the fastest at the equator, so if all the planets and the sun rotated around us, then our rotation wouldn't be so significant. New weather patterns wouldn't be good for crops. Humans would have evolved differently from what we are like now. We'd probably be shorter and stockier since gravity is so strong. And because of the soaring temperatures, we'd probably live in caves all around the world. The strongest ones would have migrated to the mountains. We'd probably have the same evolutionary path as we do now, but other physical features might be different. Our pigment would likely look different to combat the heat. The desert fox has large ears for hearing out predators and for cooling itself down in the scorching desert heat. It's possible that we would also have bigger ears than what we have now for the latter reason. We'd be a lot stronger than we are, and our bones would be thick and tough to break. Gravity is one of the key components to developing our bone density and muscle mass. This means we would unlikely need tools for hunting. This would have delayed the Bronze Age and modern civilization as we know it. With little vegetation, standing upright wouldn't be so necessary to find predators around us. We wouldn't be the fastest runners either, but we'd be strong enough to fight off a pack of strange-looking wolves. And if the Earth was supersized, then it's possible that multiple species of humans would be roaming the land in isolated areas. Some human species would grow and evolve into the intelligent thinkers of today, but some would remain the same. And some creatures from the past would still be around, unchanged. Sharks would have been around since the dinosaurs era. They wouldn't have to change their form or adapt because of their dominance. Other animals would remain the same because of their isolation. The Galapagos Island hosts some unique animals because they've been alone for so long. Without proper predators constantly lurking around them, they don't fear humans. The new mega-sized Earth would have areas as large as Asia filled with isolated animals that could remain the exact same as when they first appeared. The human species of those regions would also remain the same, since they wouldn't have moved or experimented with anything. Their diet would remain the same, and they would get used to the climate they're in. Technology would also have flourished differently in various parts of the planet. With some areas in complete isolation, they wouldn't have access to new gadgets and inventions. It would be like living on a planet with different eras in the present day. Other areas would be so advanced, they might even be flying themselves outside the planet in search of truth and answers. Our gravity is good enough for us to live properly and develop life, but if we pumped up our size to that of Jupiter, then gravity would crush us. And being the size of the sun, Earth wouldn't even be a planet, but a brown dwarf, and would constantly be burning until it became a new sun. As of now, Earth is so small in our universe that we're practically like a grain of sand in the desert. On a cosmic level, we're an insignificant contribution to this universe.
In our solar system, most planets spin counterclockwise, but not Venus. This rebel planet decided to spin clockwise, and scientists are still trying to figure out why. By the way, why do planets rotate in general? What defines the speed of their rotation? Does the sun rotate? Buckle up and let's try to answer these questions. Venus is the second planet from the sun and the hottest planet in our solar system. Did you know that Venus is sometimes called Earth's twin? That's because it's similar in size and composition to our own planet. But that's where the similarities end, because Venus is a pretty crazy place, to say the least. For example, the weather. On Venus, it's always hot and cloudy. And when I say hot, I mean it like it's over 800 degrees Fahrenheit there. And those clouds, they're not made of water like the ones on Earth. Instead, they're made of sulfuric acid. So yeah, you wouldn't want to go outside without a really good sunscreen on Venus. If you look at the photos taken from its surface, you can see these toxic yellow clouds and cracked, desolate landscapes. And the spacecraft that captured this turned off almost immediately after sending these photos. Poor fella. But the surface of Venus isn't just some solid, dark, flat land. In fact, Venus has mountains that are taller than Mount Everest. These mountains aren't made of rock like the ones on Earth, though. Instead, they're made of a kind of volcanic material that's denser. Venus is a pretty creepy place that holds many mysteries. One of them has been puzzling scientists for years, and this is the planet's rotation. Most planets in our solar system rotate counterclockwise, but Venus isn't like the other girls. It rotates clockwise, and that's not all. It also rotates around the sun faster than it rotates around itself. In other words, a year on this planet passes faster than a day. It's almost like Venus made being quirky its life mission. But why is that? Well, scientists have a few theories. The most popular theory says that Venus was actually spinning counterclockwise like the other planets, but then something happened to flip it around. And what could that something be, you ask? A planet-sized object. Yep, astronomers believe that something huge once collided with Venus, causing it to spin in the opposite direction. You can imagine this like a cosmic billiard shot, with this mysterious huge object being the cue ball and Venus being the target ball. But we can't actually say that Venus is spinning the wrong way. There's no such thing as a wrong direction of spin in the universe. This is actually called the retrograde rotation. This is when a planet rotates in the opposite direction to its orbit around the sun. Venus, for example, has a retrograde rotation, which means that the sun rises in the west and sets in the east on that planet. So now when the horoscope says something like Mercury in retrograde, you'll know what it means. Oh, but Venus isn't the only weird one in our solar system. There are definitely some wacky ways that planets can rotate. For example, most planets in our solar system spin around an imaginary line called an axis. This axis is usually straight up and down in relation to the planet's orbit around the sun. However, some planets like Uranus have a tilted axis, which means it's almost on its side in relation to its orbit. This tilt causes the planet's poles to be nearly in the same place as its orbit. The result? As the planet orbits the sun, different parts of it receive different amounts of sunlight, causing extreme seasonal variations. For example, one pole might experience continuous sunlight, while the other is in complete darkness for a long time. Uranus is the only planet in our solar system that rotates on its side. Scientists think that it could repeat Venus's history. Once upon a time, a large impact knocked Uranus off its original axis of rotation, causing it to tilt at an angle of 98 degrees. We should be grateful for Jupiter. Its crazy gravity pulls all the asteroids and protects us from such collisions. All this is somewhat similar to tidally locked planets. Imagine going on a date with a planet, but instead of being charming and mysterious like you'd hoped, it's just staring at you with the same face all night long. That's basically what it's like to hang out with a tidally locked planet. Tidally locked planets are planets that rotate around their axis at the same rate that they orbit their star. This means that the same side of the planet always faces the star, while the other side is in permanent darkness. Being tidally locked can have some weird effects on the planet's climate and weather. The side facing the star can become extremely hot, while the other side can be incredibly cold. The atmosphere on the planet can also get pretty wild, with strong winds blowing from the hot side to the cold side. And it doesn't have to be planets only. Our moon also works this way. Did you know that we always see only one side of the moon? That's because it's tidally locked to the Earth. We can also take the dwarf planet Pluto as an example. It has a strange rotational relationship with its largest moon, Charon. They're tidally locked, which means that they always face each other with the same side. As a result, Pluto and Charon appear to waltz around a common center of gravity, creating a unique dance in space. But the oddities of our solar system don't end there. There are also planets with super fast rotations. While most planets rotate at a fairly sedate pace, some of them are sonic levels fast. Jupiter, for example, rotates once every 9 hours and 56 minutes, which means that it has a day that's less than 10 hours long. That's fast enough to cause the planet to bulge out at its equator. And also, this rapid rotation creates strong bands of winds that can reach speeds of up to 400 miles per hour. And if all this still seems logical and kinda makes sense, then how about chaotic rotations? Yep, some planets have a rotation that's so irregular and unpredictable that it's known as chaotic rotation. This is often caused by the gravitational influence of nearby moons or other planets. And it's mostly the case with moons and small objects like that. In our solar system, some moons of Pluto, Saturn, and Neptune have chaotic rotation. By the way, the Sun rotates too, just like the planets. However, its rotation is not uniform. The equator rotates faster than the poles. Pretty weird, isn't it? This phenomenon creates a magnetic field that's responsible for phenomena like sunspots and solar flares. But all this raises an interesting topic. Why do planets rotate in the first place? This may sound like a silly question, but can you answer it? The answer might be trickier than you imagine. It all started around 4.5 billion years ago with the formation of our solar system. When it formed, it started as a large cloud of gas and dust. As the cloud began to contract due to its own gravity, it began to spin faster and faster, like a spinning top. This spinning motion caused the cloud to flatten into a disc-like shape. As the cloud continued to contract, the center became denser and hotter, eventually forming the Sun. Meanwhile, the material in the disk began to clump together and form planets. But because the disk was already spinning, this spinning motion was inherited by the planets as they formed. In other words, the planets rotate by inertia. They inherited the spinning motion of the cloud of gas and dust from which they formed. This is known as the conservation of angular momentum. This is the same principle that causes ice skaters to spin faster when they bring their arms in. And that's a wrap on the wacky world of planet rotations. From the lightning-fast spin of Jupiter to the bizarre backwards rotation of Venus, it's clear that our solar system is full of surprises. But thanks to the laws of physics and the gravitational pull of the Sun, these planets continue to spin on, keeping time with the steady beat of the cosmos. Stay tuned.
Okay, show of hands. Who still believes that the Sun goes around the Earth? Nobody. Oh, but everybody used to. It sure looks like it does. The Sun comes up in the east, the Sun goes down in the west. The Sun comes up in the east again, so the Sun goes around the Earth. It seems intuitively irrefutable, and it is so. But it's not true. The Sun doesn't go around the Earth. Everybody knows that, but only now. So why do people still believe the Moon goes around the Earth? It's not true either. We have to go back over 500 years to begin to get an idea of how hard it is for science to change universally accepted facts. Nicholas Copernicus, around 1510, was the first to propose a heliocentric, sun-centered solar system, but he didn't do it publicly. Copernicus privately circulated letters to other astronomers explaining why the accepted fact of an Earth-centered solar system should be scrapped in favor of a more straightforward, more astronomically correct, sun-centered solar system. Copernicus's difficulty in promoting the sun-centered solar system depended on another bold conceptual innovation, that the Earth rotates. Copernicus's concept of a rotating Earth flew directly in the face of 5 literal statements in the Bible that the Earth was founded on a fixed foundation never to be moved. And the Catholic Church wasn't about to let that worldview be challenged or changed. Copernicus had too much to lose to go public with his revolutionary, pun intended, heliocentric theory as a churchman himself. 100 years later, Galileo Galilei wasn't so reticent. Galileo had observational proof to back him up because he had a telescope. In early 1610, Galileo first observed the moons of Jupiter and kept track of their orbits. Yes, the moons of Jupiter do orbit around Jupiter. They go round and round the giant planet in actual orbits, unlike, as we shall soon see, how our moon travels around the sun with the Earth. Galileo became famous, or infamous, as the case may be, because he discovered orbital motions that were not heliocentric, that did not fit the accepted worldview. It rattled civilization's Earth-centered cosmology. Galileo was indeed revolutionary. Later in 1610, Galileo observed through his telescope, which only had an aperture of 1.5 inches, the planet Venus going through phases, just like the moon goes through stages. Galileo wrote that Venus imitates the moon, in Latin, in his notebook. There could be no other explanation for these observations. Venus was orbiting the sun. People were afraid to look through Galileo's telescope when he set it up in the Great Square of Pisa. They were too scared to have their worldview revolutionized. Strange as it may seem, we are experiencing something similar to that now, concerning the moon orbiting the sun and acting like a double planet with Earth. People, scientists included, stubbornly persist in viewing the moon as its clever official International Astronomical Union name. It's a moon of the Earth, orbiting around the Earth, showing its different phases throughout the lunar month, or moonth, as moon fans sometimes like to call the 29.5-day cycle of lunar phases. Moon lovers' favorite day of the week, of course, is Moon Day. It comes right after Sunday. But back to the science. It's how our school books portray the phases of the moon. It's what people believe now. Notice how the Earth is the moon's center, and how it goes around the Earth in a circular path. This is the geocentric view of the moon. It's what we see from Earth. The moon comes up, the moon goes down. The moon comes up again. The moon goes around the Earth. But that's not what's happening in space. It's way past time we Copernicus-size the moon. We need to start seeing the moon from a heliocentric point of view, as we do for everything else in the solar system. First of all, the geocentric view of the moon's phases shows the Earth stationary, sitting in the center of the moon's path for a whole month. But the Earth is not stationary at all. We're zooming around the sun at a very high speed, anywhere between 66 and 68,000 miles an hour. Therefore, any picture of the moon going around a stationary Earth is profoundly misleading and really outright wrong. The heliocentric view of the Earth and moon moving together in space should look something like this. Notice that the moon is not going around the Earth. It's traveling along with the Earth, around the sun. The path of the moon around the sun is a sinusoidal path back and forth, across the ever-forward moving path of the Earth. Notice that the moon always goes forward too. It doesn't ever go backward to either the sun or the Earth. By always moving forward and sinusoidal, the path of the moon does not qualify as an orbit in the same sense that the other moons of the solar system orbit their planets in elliptical paths. Therefore, it is wrong to say the moon orbits the Earth. The moon orbits the sun along with the Earth, or the moon and the Earth both orbit the sun, are statements Copernicus and Galileo would approve of. But science today has difficulty accepting a heliocentric view of the moon. Maybe there would be too many books that need to be reprinted. Maybe too many astronomy professors would have to admit that they were wrong their whole careers. Accordingly, objections are put forward to block the revolutionary heliocentric view of the moon from being universally accepted. One such objection is that the moon never leaves the Earth's gravity well, and therefore should be rightly considered a moon of the Earth, an orbital, to use the astronomical term for satellite. Undoubtedly, the moon never leaves the Earth's gravity well, or else we would lose the moon. However, representations of this well-known definite fact always show the moon moving around the Earth inside the gravity well, and this is not true. The moon never goes back toward the Earth as it would need to if it were in an elliptical orbit. So the gravity well objection can be dismissed because the astronomers who propose as orbital evidence that the moon always stays within the Earth's gravity well fail or neglect to include the facts of the moon's continuously forward sinusoidal motion. Escape velocity for the moon to leave Earth's gravity well is reported to be about 2,684 miles per hour. Relative to the Earth, the moon presently moves about 2,238 miles per hour. What kind of impact would it take to accelerate the moon that extra 450 miles per hour needed to knock it out of Earth's gravity well? If anyone wants to compute that, You're most welcome to put your answer in the comments section. Maybe it could happen, and that would not be good. There's another objection to looking at the moon from a heliocentric point of view. And that involves the barycenter of the Earth-Moon system. The barycenter is the center of gravity between the Earth and the moon. Think of yourself on a seesaw in the park. The other end of the seesaw is a massive lineman from a professional football team. How far forward towards you would the lineman have to move so that you both are balanced evenly? He'd have to move towards you almost to the center of the seesaw. You are the moon, and the lineman is the Earth, although Earth is a feminine name. The balance point of the Earth-Moon system, the barycenter, is over 1,000 miles inside the Earth. It is this balance point, astronomers dutifully point out, that is orbiting the Sun. It is a heliocentric point of view. Copernicus and Galileo would approve. However, these astronomers always seem to add the geocentric animation of the moon orbiting around the Earth, with the barycenter inside. In this way, they can keep the moon orbiting around the Earth. But it's somewhat dishonest to combine two different perspectives in one animation. You can't have your cake and eat it too. This leads us directly to the real sticking point that keeps us from believing that the moon is orbiting the sun, the double planet conundrum. The International Astronomy Union refuses to consider the moon and Earth a double planet. They refuse to do so almost exclusively because the barycenter of the Earth-Moon system is inside the Earth. It's tough to buck City Hall, as the saying goes. You'll recall that IAU, or UAI if you use the French designation, demoted Pluto to dwarf planet status, and they still haven't reversed that decision, despite seemingly ample evidence that Pluto is the 9th planet. Perhaps we should reflect on what it means to be an Earthling. To be an Earthling implies that we know ourselves to be space-borne people orbiting a yellowish star near the outskirts of a spiral galaxy. We, meaning all the peoples of Earth, live in space and are absolute creatures from space. Above us is the moon, Earth's companion. We're making a big mistake by referencing the moon according to our geocentric parameters. Our conceptual expansion into space is inhibited by an incorrect, outdated, earthbound view of the moon. The universe doesn't revolve around us, and neither does the moon.